Hello everyone and welcome to another video. So today I'd like to have a discussion on the gradient of a function and the directional derivative. So these are actually pretty simple ideas, but they're incredibly powerful and useful, and you see them all over the place in engineering, science, and math. So let's just jump into it. We'll start with the idea of what is the gradient of a function. So let's consider a scalar function of n variables. So you have basically n different independent variables or inputs to this function. Let's call them x1, x2, all the way up through xn, right? You pass those different n variables into the function. This function does something to it, right? And it spits out some scalar number, right? That's the idea with the scalar function, right? We had a dedicated video discussing scalar and vector functions, but again, this is pretty much the simplest idea that you could have, where you've got a function, n things go in, one thing comes out, right? Okay, so that's the idea with the function. Now let's ask ourselves, what does it mean to have the gradient of the function? So the gradient of this function f, it's really nothing more than a stacked up vector of all of the partial derivatives of f with respect to each of these n independent variables, right? So all you do is you take the partial derivative of f with respect to the first independent variable. That's this first entry of the vector. The next entry is the partial of f with respect to x2, all the way down to partial of f with respect to xn, right? So this vector, you can see, it is an n by 1 vector, right? Or a 1 by n, depending on how you wanted to write it. I always like to think about this as an n by 1 vector, right? I like to stack things up vertically, but it really doesn't matter. Depends on your application, but it's nothing more than a stacked up version of the partial derivatives in vector form. So a lot of times what you're going to see this written is as just grad f or del or nabla f, right? Now, the thing that we would like to mention is keep in mind, right, that this vector, right, this is going to be a function of the input parameters, meaning depending on where you are in this function, this vector value is going to change. So to better denote that, what sometimes I like to think about is, let's use the notation of, you have all of these n independent inputs. Sometimes I like to think about these as all coming in as a big x bar, right? So again, this is an n by 1 vector, right? Again, all there are is just n different independent inputs. You could just stack these up as a vector, right? So this function here is really, I could write it in compact notation like that, right? Same thing with the gradient, right? By the time I take the partial of all of these, this is going to be a function of the input vector x. So I'm going to use the notation x, like this, or like this, or like this, right? And again, all this is reminding us is that this gradient vector, it's going to change, its value is going to change depending on where in the state space or where, what values of the independent variables you have, okay? I think the easiest way to look at this is maybe with a concrete example. So let's come over here. Let's consider I've got some function. In this case, it's just two independent inputs, right? You can think about f, right? It's just you give it two things like an x, y position, right? And all this thing does is it calculates, you know, like a z and like an altitude or a height. Okay, and the way it does this is it takes 3x squared and then adds it to y cubed, right? That's what the function does, right? Here's the picture, okay? So again, two inputs, one output. What I can think about doing now is calculating the gradient of this function f, and all I'm going to do is take the partial of f with respect to x1. So take the derivative of this thing with respect to the first independent variable, which is just x. So you can see here you get 6x. Then the second entry is partial of that function with respect to the second independent input or variable, which is y. So partial this with respect to y, you just get 3y squared, right? So again, here is the gradient, and again, maybe what we should do is use the notation that this is a function of x. And you can clearly see that here, right? The first input, second input shows up in the gradient vector. So we have to consider a point. If we want to actually draw a vector or look at a concrete instance of it, I have to pick a location in xy space that I want to look at. So again, if we're thinking about this as just being an x position and a y position, I have to pick a point in the plane that I'm interested in. So, you know, if we have something like x and y, let's pick a point. Let's pick a point of, how about x of -3 and y of positive 2, right? So I'm interested in looking at this point right here, okay? So I'm going to pick this point, negative 3, positive 2, okay? And now what I can start talking about is now I can ask, what is the gradient of the function at this particular point P, right? So it's just this gradient, but I'm going to look at it at a very specific x and a very specific y, namely these two values. So this is what you end up with, right? You just plug in the numbers and you get the gradient looks like this. So in this particular case, it seems to point in this direction of negative 18 and positive 12. So I don't know, I'm not going to draw this very well, but you know, it's like something like in this direction, right? So here is the gradient of f at the point P. Right? And you can see as you move this point P around, right, this gradient vector is going to point in different directions, right, depending on where you are and where you evaluate the gradient, right? Okay, so what might actually help to get us a little bit of an intuitive feel of what this means is let's go plot this actually maybe in Matlab where we can visualize the function f, we can visualize the point, we can visualize the gradient vector, all this stuff, and see what does this physically mean? What is this telling us about the function? All right, so here we are in Matlab. Here's the point that we're interested in, this negative 3, positive 2. I've just wrote myself a little function here called visualize gradient that you can kind of see on this side where all we're going to do is, you know what, let's step through this code and we can just take a look at what would be helpful. So I've gone ahead and started a figure. In fact, let me go ahead and dock this figure so we can see all these different objects as we build them up. Okay, so the first thing I'm doing here in the function, right, is I'm just going to go ahead and define that function or the surface that lies on top of all of the possible xy locations. So in this case, I'm just looking at xy values between negative 5 to positive 5, and we are just going to evaluate the function at all of those different locations. And again, what that's going to define is a three-dimensional surface. Again, we've got a dedicated video talking about plotting in 3 dimensions, so if you want to look at that, feel free to check out this video over here to talk about 3D plotting in Matlab. But conceptually, all we're talking about now is evaluating the function at all of the different xy combinations, and as you know, that's going to create this surface plot on top of all the possible xy locations. So I'm going to do that right here. So let's go ahead and step through this, and here's what this function looks like, right? So down here in the xy plane, there's all these possible different inputs, all the possible independent variable or parameters that go into the function, and for each of those pairs, you get a corresponding, in this case, let's think about it as a z value or an altitude. If you want to think about this as like a terrain map or something like that, this is basically telling us what the terrain looks like. And you can see it's this sort of bowl-y, kind of sloping kind of object, right? Okay, so that's what the function looks like. Now what I'm going to do is let's plot that point of interest, this negative 3, positive 2 location. So if I go ahead and execute this line now, we get this point down here in the xy plane, right? So this is the point of interest down here in the xy plane, okay? What might be interesting is let's plot this exact same point of interest, but let's trace it up to the surface, okay? So that's all I'm going to do right here with this next line of code is I'm going to go ahead and plot as a circle that corresponding location in now terms of x, y, and z, right? And what we would now like to do is let's plot the gradient vector, right? And in fact, I'm going to plot a scaled version of the gradient vector. Notice here that I computed the gradient vector, and I'm just going to divide it by 10 just so the gradient vector isn't super duper long and pointing off to a large direction. So I'm going to go ahead and just chop the length down by a factor of 10. Okay, so let's plot that now with this next block of code, and you can see here it is. So this orange line down here in the xy plane is the gradient vector, and if you line these up on top of one another and we look sort of straight down, you get an idea of what's going on now, right? The gradient vector is pointing in the direction in which the function increases in value the most quickly, right? So again, let me plot one more thing. I'm just going to draw a magenta line connecting these two, the X and the O, just to make this a little bit easier to see. And there we are. So here's the picture that goes along with the example we had on the board, right? So we picked a point down here in the XY plane. We picked a location in the input space, right? All the independent variables define what goes into the function or what are the inputs of the function. And now what the gradient is telling us is at this point, if I want to increase the function value or climb up this curve or go up as quickly as possible, which direction do I need to head? And apparently it's in the direction of this orange line, right? And again, I think now you see why this gradient vector will change depending on the point of interest, right? In fact, I've got a little animation down here that's going to show that. Let me put another breakpoint in here. And in fact, let me take off some of these other breakpoints inside my visualization function, because all I'm going to do now is let's go ahead. I think I can close this figure. Yeah, let me close this figure and let me dock the new one. And we're going to watch what happens as we go through this. Okay, so all I'm going to do is I'm going to just start moving the XY, the point of interest, right? I'm going to move that around and we're going to see what does the gradient look like, both from a isometric kind of point of view and from a sort of a top-down point of view. So that's what I'm doing right here. So let me go and just run this code and you can see, look at this, right? As you move around, right, the gradient vector changes both in direction and magnitude, right? Because now we see what's clearly going on is the gradient is telling you at any given point which direction do you want to head to increase the function value as much as possible. And furthermore, at some locations, the function value increases quicker than others, right? You can see there are some of these really steep sections, and as you can see in that case, the gradient magnitude is larger. And then there are some sort of flatter regions kind of out here on the edges, and that's exactly what you're seeing, right? The gradient vector is smaller, but in all cases, right, the gradient vector points in the direction of maximum function increase, right? So again, here's the isometric view on the left and the top-down view on the right, okay? And now I think this is giving us a good intuitive feel of what the gradient does. And again, I find it's very helpful to think about this from a perspective of, you know, I like to go hiking and I like to go out in the mountains, and you see all these topographic maps of regions, right? And now we understand that what the gradient calculation is doing is if you have an analytical description of this function or this complicated terrain, if you calculate the gradient at any given point, it is telling you the direction in which to travel if you want to climb up as steeply as possible. And the nice thing that I think we should probably take a look at is keep in mind that this is telling you the instantaneous function increase value at the point of interest. If you keep walking along this direction, there's no guarantee that the function is going to continue increasing. In fact, in this example, you can see right here, if you keep walking on this, you're climbing up this little ridge, but eventually if you keep going in the direction of the gradient, the function value actually starts going down, right? Because you come down the other side of the ridge and you're going to start falling down. So again, the thing to keep in mind is the gradient is going to tell you the direction of maximum functional increase, but it is only telling you at the point of interest. You have no guarantees of what the function is going to do as you move away from that point. Okay, so that brings us to our next discussion, and let's head back to the board for the next topic. All right, so we can build on this idea of the gradient to discuss now the directional derivative. So the idea with the directional derivative is that I would like to now examine the rate of change of this function f at some point p, but instead of looking at how that function changes in the direction of the gradient, I would like to go in some other direction given by some other vector b. And this is what we mean when we say this is the directional derivative. This is the directional derivative of the function f at the point P in the direction of B. So that's a lot of things, a lot of symbols going on, a lot of things that are needed to compute this. So let's write this like this. The directional derivative of the function f in the direction of the vector B. What this is defined as is you want to understand how is the function changing at the point P as you move in some direction B. So you can think about this almost as like a rise over run, right? You're looking at a change in the function value for a change in the distance, and the distance that you're going to go is in some direction along with this vector B. So you can think of it as the function value at some new point Q minus the function value of where you were at the point P, right? This is the sort of the rise, right? and then the run is the distance that you go, and we're going to now look at taking the limit as this distance goes to 0, and right, and we're going to define that as a directional derivative. So the picture that goes along with this, right, is, again, you've got some function f, right, that's shown by these contour lines here. You pick some point P, right, this is where I am, and now we saw in the previous discussion that the gradient vector, this orange vector, is going to point in the direction of kind of the maximum uphill direction, or the maximum function value increase direction. But now, instead of going in this direction, I'm going to pick some other direction, this green vector b, which could be any other direction, right? And now all I'm going to do is I'm going to look at some point Q, which is a distance s away from point P along this vector b, right? So I'm just going to walk this distance, right? And now, as I take this s distance and shrink it down to 0, you can see how this terminology of this rise over run is basically telling us and giving us how much the function changes for a given distance in that direction, right? So that's the idea or the concept of the directional derivative, right? It makes physical good sense, especially if you look at it in this context. But now let's ask ourselves, how can we actually compute this, right? So the way we can compute the directional derivative of f in the direction of b is by dot producting the vector b with the gradient vector, right? And again, let's make a small little asterisk note here that this is assuming that b is a unit vector. And again, since b is just giving you the direction of where you're heading or where you're investigating, you can easily normalize that, right? So if it's not unit linked, just go ahead and make it unit linked. So again, this is the function or the description of how to compute it. It's really simple. It's take the dot product of two things. Take a dot product of the unit vector b in the direction that you want to head, and take the dot product with the gradient. Now, again, we got to remember, the gradient, as we just saw, this is a function of where you are, or the point P or x, however you like to think about it, right? The vector x. It's just basically asking, you know, where in this independent variable space are you? And that's where you want to compute the gradient. So again, maybe to make the notation a little bit more complete, we should note that although b is fixed, right? B doesn't change, it's just the direction that you like to head. The gradient changes as a function of x. So this directional derivative is also a function of x or the point P, however you like to think about it, all right? Okay, so again, really easy to compute it, right? And it makes physical intuitive sense, right? Because if you recall from our discussion on dot products and scalar projections, right? What the dot product is effectively doing is that it's measuring how aligned two vectors are with one another, right? So this is effectively asking us how aligned is the direction that we're interested in heading with the gradient vector, and that's going to tell us effectively how much is the function changing as you move in that direction, right? So let's consider an example of this. Let's say, like, how about the room that we're sitting in right here? Let's say the temperature varies, right? If I move in x, y, or z dimensions, right, the temperature is different in all of these different locations, right? So let's describe that temperature variation by this function right here, 4xy plus z squared, right? Now, I'm going to consider, let's pick some point in this space, x of 2 units over, y of 1 unit, and then z of -1 unit, right? So some point in space. And let's assume that maybe we've got a little like drone or something like that that is located in this at this point P, okay? And the temperature, you know, it feels some temperature right here, and if it doesn't move, the temperature is constant, right? But now I want to ask the question, what if this thing moves? If this drone moves in this direction B, right here, this vector of 1, -2, 1, again, I don't know where that's pointing. Maybe that's like moving like this, you know, or something. It's a little bit arbitrary. It doesn't really matter, right? It's just some direction it's going to move. So the temperature is something right here. It's going to start moving in this direction. And now I'm going to ask, what's the rate of change of temperature per unit movement of this vehicle if it goes in this direction, right? Okay, so let's just use our formula to calculate it, right? So the first thing we're going to need to get is the gradient of the temperature at the point P, right? The point that we're interested in. So that's pretty easy. Let's go ahead and compute the gradient, right? I just take the partials of this function with respect to x, y, and z. You get this. This is the general gradient, right? And now I want the gradient at this point x naught, or p. You know, sorry for the switch of notation, but all we're asking for is evaluate this gradient at this location. So everywhere you see an x, plug in 2. Everywhere you see a y, plug in 1. Everywhere you see a z, plug in -1. So if you do that, you get this vector right here. So this is the gradient vector at this point p, okay? Now, all we're going to have to do now is plug it into our equation up here, with the caveat that, again, make sure that this direction that you want to head in is a unit vector. So in this case, I can see from inspection this is not a unit vector. So what I'm going to do is I'm going to normalize it so that the whole thing here that I am dot plotting with the gradient, this has to be a unit vector. So I take, you know, here's a vector, and I'm just going to divide by its length, right? Then I can dot product that with the gradient, okay? And at the end of the day, what you run all these numbers, you get this thing, minus 5.715. What does that mean? What that is telling us is that if the aircraft or the drone or whatnot is sitting at the point P and it decides to move in this direction B, what it's going to feel or discover is that the temperature is actually reducing. It's going down by 5.71 degrees per unit length. So assuming this is a right, because this is describing the temperature with units of meters, right? X, Y, and Z are all in units of meters or some length. So it's basically saying the temperature is going down at 5 degrees per meter of movement, right? So maybe what might be helpful is, instead of me just waving this around, let's jump over to the computer and let's visualize this temperature, visualize the direction, and we'll see what this all looks like. All right, so I've got this visualized here in Mathematica just to give us an idea of what's going on. So what I've done here is I've tried to plot the isotherms, or the surfaces of constant temperature. So this blue surface here is all the places where the function is f is equal to 5, or 5 degrees, I guess, if you want to use that. Remember, this was our temperature map, right? And then the yellow curve is where f is equal to 10. So at all these yellow surfaces is 10 degrees, so it's a little bit warmer. And then finally the red is 15 degrees, so even warmer yet again. So again, you see that the temperature profile in this volume is somewhat complicated, right? And now what I've done here is I've plotted with this green dot the point P that we're interested. So this is where the drone is located in the environment, right? And what we're seeing now is I'm plotting in magenta. This is the direction B. Okay, it's the direction in which we would like to travel. And as you can see, what's going on is where the drone is located, if it moves in the direction of the magenta arrow, you can see that it's getting cooler. It is getting colder, right? Instead of being near this yellow surface, we're moving towards the blue surface. So yes, the drone, if it moves in the direction B, it's going to start getting cooler, right? The temperature is going to go down, or the function value is going to decrease in that direction, right? And again, for just completeness, I've gone ahead and drawn the gradient as well as this green vector. And as you can see, the green vector tells you at that point, again, we're climbing uphill in the steepest way possible. So you can see that it's giving you a direction which is almost normal to this isotherm, this yellow isotherm surface. And it's trying to get over to the hot red surface as quickly as possible, right? So you can see that this is what the directional derivative is telling us. It's telling us that if you want to move in some direction other than the gradient, it's going to tell you if the function value goes up or down. And I think this is a nice visualization to hopefully illustrate what that example was showing. Now, this idea now kind of leads to our next question is, well, if you can move in any direction, where should you move if you want to go, if you want the function to increase or decrease as quickly as possible? All right, so we've got our directional derivative here given by the dot product, as we saw, of the direction and the gradient. So now, as we suggested earlier, we should ask ourselves, which B should you pick, right? If you have all these different directions you can choose, which one yields the largest increase, or I guess conversely, which has the largest decrease, right? So you see that the directional derivative, it's the dot product of two vectors. And again, remember from our discussion on dot products, right? The dot products of any two vectors, right? The way you get this is you can also compute this dot product as the length of u times the length of v times cosine of the angle between them, right? Where theta, again, is this angle between them. So what we see is that, cosine varies between +1 and negative 1, right? And the way you get a positive 1, right, is if cosine of theta is, if theta is 0, right, then cosine of theta is 1. So what this tells you is that you want to choose u and v to be in the same direction. That's going to make this dot product as big as possible, right? So to maximize this directional derivative value, you want to choose b in just, it's got to be in the same direction as the gradient, right? Which again makes perfectly good intuitive sense if you go back to our discussion of, climbing uphill, the gradient points an uphill. So if you want to increase the function value as much as possible, just go in that direction, right? That's all this is saying. Now, conversely, what's interesting is, all right, what if you want to go downhill as fast as possible, or if you want the function value to decrease as much as possible? Is there some b value that is going to help you, or some b vector that's going to help you to go backwards? And again, you come back to this discussion of the dot product being the cosine of the theta coming in here, right? So this is the thing I can change, right? So by changing the direction of, right, I want this cosine to be a negative 1, right? And again, the way you get that is if theta is some multiple of pi, right? Pi, 3 pi, 5 pi, something like that. Basically, you want them, you want the vector pointing in the opposite direction, right? So you want the angle between these two vectors to be as large as possible, right? Or, well, not as large as possible, but 180 degrees, right? So we see that the other way to think about this is if you want to minimize this directional derivative, you choose b to be in the opposite direction of the gradient, right? So again, just to formalize that discussion, right, here we have this, right? So you're going to want to choose b to just be in some direction the same as the gradient, right? As long as this alpha is positive, right, this is saying b is pointing in the same direction as the gradient. And if that's the case, you maximize this directional derivative. And if the alpha is negative, you minimize that directional derivative. So again, fascinating. I want you to keep this in mind because this idea, again, it makes pretty good intuitive sense that if you want to increase the function value, go in the direction of the gradient. If you want to decrease the function value, go in the opposite direction of the gradient. This is one of the key ideas for optimization, numerical optimization routines. Gradient descent is all based on this idea. We're going to talk a lot about that in future discussions when we get to the topic of optimization, but this is kind of the framework of it. So, with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. If you scroll down and click on that subscribe button, it really does help me continue making these videos. And remember, the new videos come out every single Monday, so I hope I'll be able to catch you at one of these future discussions, and we can all learn something new together. So, until then, I think I'm going to sign off. Talk to you later. Bye.